Good morning, good afternoon, good evening, wherever you might be. In this video, I would like to talk to you about Anderson localization and complexity. Gell-Mann worked on fundamental particle physics, and Anderson worked on quantum materials science. They supposedly hated one another. They're both dead now, but their conflict has scarred the landscape of physics for the past 60 years. Whereas Gell-Mann's fundamental particle physics corrupted the physics narrative by digging a single, deep chasm of reductionism in a complex Rube Goldberg machine language that very few people can parse well enough to understand why it is inconsistent with general relativity. Anderson's quantum materials science achieved a similar level of linguistic corruption and confusion by cultivating a vast garden of anti-reductionist, complexly redundant holes that localize the energy of a wave in different ways depending on how the holes are distributed. This complexity seems to have been methodically protected and increased by a community that rebrands and renames the same concept over and over again. In metals, you have Fermi gas, band theory, DFT, BCS, topological insulators, Landau level physics, fractional quantum Hall, Hofstadter model, Ising model, Luttinger liquid phonons. And in glass and fractals, you have percolation, amorphous systems, random topological insulator, fractal topological insulator, Kondo effect, percolating Hofstadter butterfly, Anderson localization, topological Anderson insulator, fractional Kondo effect, many body systems, and frustrated systems. This all can be expressed in terms of ill-condensed matter, and if you look at the blog post, you'll see a link to a book that costs more than $100, and it's called Excursions in Ill-Condensed Matter. And I'm not sure if they intended for the title to be funny or not. What you see in this book are theories that have been renamed and reformulated by modern physicists who like to name things after themselves whenever they worry about the effect of impurities in an optical material. Instead of consolidating a zoo of languages that had already degenerated, the community pursued further degeneration. All of the different brands or formalisms or languages in this field are different ways to describe how waves flow through an object that has some holes in it. And way back when I was just an undergraduate writing an undergraduate thesis, I made pictures of how these waves would flow through a material with holes. And when I Google that topic today, I see the present generation of physicists making the exact same pictures that I made, but each different research group is explaining it in their own private language. It is a very strange degeneracy of modes. There has been no incentive to consolidate the languages that emerged after the first nuclear bomb was detonated and the Tower of Babel fell. In fact, the present system seems to encourage degeneration. It makes me nostalgic for simpler times. I long for simpler times in physics and simple questions in plain universal language, such as why is cheese full of holes and why is the sky full of stars? It might very well be for the same reason. Holes form in cheese when little bits of hay fall into the milk, allowing a small colony of bacteria to collectively release carbon dioxide. Stars form in the sky as a form of condensation around an impurity or inhomogeneity, much like hot breath on a cold night. This is similar to how hot spots form when waves propagate through an inhomogeneous optical material, like so many traffic jams in a city or bubbles in a bottle of beer. All of these systems are described by how energy interacts with whole structures, and since writing about a group of wholes in 3 dimensions is rather challenging, physicists typically start with 2 dimensions, or even 1. Consider the spectrum of a light pulse that passes through a window. It has this sort of bumpy structure, a periodic bumpiness. And in technical jargon, we would say that this spectrum is channeled. And there was a nice equation for this process in a 1970 PRL by someone named Lodenquai, but I, for some reason, can't find that very easily. You might expect the spectrum of a light wave going through a pane of glass to be smooth, but it is bumpy. So why is that? It turns out that the light bounces off of the internal surfaces of the window back and forth, and different wavelengths are reflected at different angles. This can be described analytically with a simple equation that I can't seem to find. I believe that the derivation starts off with Snell's law. To get a sense of what this process looks like in more dimensions, I'll think about how light propagates in a thin, inhomogeneous film, like a pane of glass with metal grains spattered across it. The technical jargon for this sort of system is given in terms of phonons and surface plasmon polaritons, but I'd like to connect it to the intuition from the simple channeled spectrum that I saw described by Lodenquai. I imagine total internal reflection off of a single impurity, like a droplet of glass or metal, and then I imagine total internal reflection off of a network of these impurities, as in a rainbow formed by scattering off of drops of water. For certain wavelengths, this leads to a bumpy spectrum with frequency minima defined by the diameter of the impurities and the spacing of the impurities. I messed up. Okay. The equation used for this renormalization process is notably similar in form to that of Lodenquai's channeled spectrum equation. Say you have a grid of points, and each point is randomly assigned to be metal, conducting, or dielectric, non-conducting. This grid represents a collection of metal droplets scattered randomly on the surface of a piece of glass. If you shine some light on this random metal dielectric thin film, electric currents will be excited within the metal grains. This excitation is described by Druda's theory. If the wavelength of the incident light is larger than the diameter of the metal grains, the currents will try to flow between the metal grains, and Druda's theory won't work anymore. If the wavelength of the light is larger than the size of your grid, the current will try to flow from one side of the grid to the other, and it will become concentrated at bottlenecks, or hotspots, which connect the different points on the grid. At these bottlenecks, the electric and magnetic fields will become very intense, and if you want to calculate what those fields will be for different amplitudes and wavelengths of light, you need to use renormalization, something that many physicists seem to think is confusing, but it's really mathematically quite simple. In a real space renormalization technique, you apply a voltage to each segment of the grid. This voltage represents the amplitude of a light wave. Then you calculate the average voltage over a slightly larger segment of the grid by using an electric circuit called a Wheatstone bridge. This is something that engineers would know all about. After doing this for each subsegment of the grid, you repeat the procedure for even larger segments of the grid. Repeat this until you have calculated the average voltage for the entire grid. Next you reverse the procedure in order to solve for the currents which will be excited at each individual grain of metal for different wavelengths of light. From the local currents, you can calculate the local electric and magnetic fields. This is all classical, yet the theory predicts discrete and huge local field enhancements, which can become non-physical unless some sort of nonlinear damping or quantized radiation process is added to the model. If you want to dig into the details, it helps to understand the limitations of Lorentzian Maxwell's equations, and to understand the features of Galilean Maxwell's equations. Something similar to this could be combined with the equations from gravito-electromagnetism, the theory from the 1800s, Heaviside, and it can be applied to systems of stars or galaxies for which you want to know the local gravitational fields. However, things get more complicated when you move from a two-dimensional film up to three spatial dimensions. A random walker in 2 dimensions will return to the origin an infinite number of times in an infinite number of steps, but in 3 dimensions he will wander away and never come back. This is just one of many types of renormalization, and it is a little bit different from the renormalization you often hear particle physicists talk about when they complain about the infinities which arise when they try to quantize gravity. I learned about this form of renormalization about 16 years ago from some papers written by Sarychev and Shaleyev in the early 1990s. At the time, I was reading a book on nonlinear optics in inhomogeneous materials while searching for information on Anderson's light localization and trying to understand how light could have one spin in 3 dimensions and another spin in 2 dimensions. At that time, it was confusing, but now it's embarrassingly simple. It was my first exercise in modeling a system in multiple, distinct, equally true languages, the languages of Maxwell's equations, electric circuits, and polarizabilities. If you are interested in digging into these matters, you might want to click on the blog post and find some links to some of the things that helped put the puzzle together for me. I never did get a sense of what this process looks like in 3 dimensions. There I see a similarly channeled spectrum with frequency minima defined by the diameters and spacing of the impurities. Renormalization algorithms in 3 dimensions are trickier than in 2 dimensions, but sensible approximations can make them workable. As I said earlier, gravito-electromagnetism helps, Galilean Maxwell's equations help, and Landau's work on superconductivity helps as well. This should all be related to a frequency comb of fundamental forces, because the strength of the fundamental forces is related to the whole structure of things large and small, in a self-similar pattern. In other words, it is related to the spectrum of the diameters of the impurities. What might Anderson have said about what I've told you right today? I think he would have disapproved. He would have said, "But you mustn't give in to the temptation to believe that a principle that works on one level will work at all levels. You never understand everything. When one understands everything, you've gone crazy." And my guess is that if you start to understand everything, people will call you crazy. Because physics is not allowed to be simple and clear. If you think it is, then you must be crazy. Oops. And you might wonder, is this education or psychological warfare? I think this would be an ideal strategy to win an invisible war to suppress knowledge. So, if it is psychological warfare, they probably took some lessons from some old Chinese proverbs. Deck the tree with false blossoms. Through the use of artifice and disguise, make something of no value appear valuable. Physics jargon, for example. Deceive the heavens and cross the ocean. Mask your real goals with a fake goal until your aims are achieved. The goal is to keep smart young people busy so that old people can hold on to power. Feign madness, but keep your balance. Hide behind the mask of a simpleton to create confusion about your intentions and motivations. Kids are easy to trick. Besiege Wei to rescue Zhao. When the enemy is too strong to be attacked directly, then attack something he holds dear. Rob, replicate, and replace knowledge until it is indecipherable. Exchange the roles of host and guest. Usurp leadership in a situation where you are normally a subordinate. When knowledge is power, politicians think they are in control, but really. So, based on this perspective, my hope for the future diminishes every time I see a popular science headline, like, for example, this one. 3 black holes orbiting each other can't always go backwards in time. So this is supposedly a discovery of some brilliant student. But if you understand what this actually means, it's only an amazing discovery if you have no objective sense of what a black hole represents. Perhaps in this case it represents an intellectual whole that absorbs the efforts of gullible students. But in this, if we think about a black hole as something that literally physically exists, and you think of it as a particle or a whirlpool, the mystery of why 3 black holes orbiting each other can't always go backwards in time, it becomes absurd. So when a whirlpool is swirling clockwise, people will say that time is flowing forwards. When it is swirling anti-clockwise, people say that time is flowing backwards. When 2 whirlpools orbit one another, they are necessarily rotating in opposite directions because otherwise they would repel one another. That is what physicists mean when they say that a black hole binary has time reversal symmetry. Time is flowing backwards and forwards in equal measures if you have 2 black holes. You should be able to do this dance like this. Okay, so here, these are attracting, and then if they're going this way, they're repelling. You should be able to feel that and have a vision of that in your head whenever you think about particles, black holes, anything. And if you can't, you should choose a different career. You should not be a physicist. If physicists understood what they meant when they said there is time reversal symmetry, they would not be surprised in the least that adding a 3rd black hole breaks time reversal symmetry. 1 plus 1 equals minus 1 plus 1 minus 1 equals 1. Oh my God, it's amazing. We should write a front page news story about it. 1 minus 1 minus 1 equals -1. Oh my God, front page news. We must write a 10-page paper about this finding and publish it in the Physical Review. Call the editors of Nature. So based on this sort of distance perspective, once you get your head out of the sand, you stop studying individual grains of sand within physics, you start to see that things like Anderson's contribution to physics, okay, you start to see these sorts of errors of myopia. Anderson, his big contribution to physics was based on exploiting this sort of myopia and these sorts of broken symmetries. He would befuddle audiences with no sense of objective reality by telling them that random motion is symmetrical and that the instant ordered motion occurs, an asymmetry has occurred. He could have explained this in the equivalent language of entropy or disorder, but instead he based his career around finding new, convoluted ways to say old, obvious things. And I think he based his career around finding new ways to cause the language of physics to degenerate by encouraging people to name things that are fundamental after themselves, for example, Anderson localization. Any respectable physicist would protest at this point and insist that Anderson's work in the 1950s on light localization in semiconductors paved the way for two brilliant ideas that have won Nobel Prizes. He inspired Josephson of the Josephson junction and Higgs of the Higgs particle. And I encourage you to click on the links in the blog to my articles about the Higgs particle, that little boondoggle. Anderson explained those concepts in terms of symmetry breaking, and I would explain them in terms of lightning strikes, magnetic monopoles, and Galilei and Maxwell's equations. The trouble I find is that if you really understand any of these concepts in detail, you will understand why they are stupid and why most brilliant ideas are overcomplications of something stupidly simple. And that whenever someone calls you brilliant, they are usually obliquely implying that they think you might be very stupid or very smart, but they can't decide because they aren't sure what you are talking about. This causes the brilliant person to constantly wonder if they actually know what they are talking about, or if they are totally nuts. After many years of testing, some brilliant people gain enough statistics about their own thoughts to make a decent guess about their accuracy. Some do not. If you are a person who is often referred to as brilliant, you probably think that normal people know something about how to be normal that you don't know. I believe that Anderson had some awareness about the limitations of brilliant people, and that is why he put the brakes on a major boondoggle called the superconducting supercollider. Perhaps he didn't think it was the right time to build another jobs program or sponge for brilliant people. Maybe he thought it would be kinder to allow brilliant people a chance to become normal rather than enable their brilliance. I mean, you have a choice in life. You could invest your energy into becoming more brilliant and focused, or you can invest your energy into becoming more pleasant to be around, agreeable, social. It might be harder to do something that isn't naturally what you like to do, but it's possible. So, for example, I decided to try to do physics because it wasn't something I naturally liked. And I thought I needed to balance myself out to do something that didn't fit with my natural tendencies. But as that process went on, eventually my natural tendencies, like 20 years later, I said, I've had enough. And now I'm trying to recover who I was before that 20-year reprogramming process. So now I would like to help serve as a cautionary tale for those who are considering allowing themselves to become heavily programmed by a system that might not be what you think. So, when Anderson testified to Congress in opposition to the superconducting supercollider project, he was reviled by particle physicists as acting in support of an anti-science movement. his colleagues actually tried to put him in the same box as creationists. And since I might also be tarred and feathered in a similar way for my criticisms of the scientific community, I appreciate his response to this criticism. He said, "There have been yahoos in every period in American history. I don't think there is an effective anti-science movement. If the religious right get into power, we'll have to defend a hell of a lot besides science." And I think that's right. The religious right have come into power in many areas of today's America, and there is certainly a strong anti-science sentiment, but I don't think the response is to fight this. I think it is to, try to get along with people and not to worry about it too much. Because boondoggle science projects continue to get funded because even the religious right doesn't want their district to lose any federal money flowing into their state. What worries me more is the religious fanaticism with which the scientific community has defended itself from criticism. I think this is highly counterproductive because what you want to do is convince regular people and the religious right that scientists are sensible people and that they are perfectly happy to separate their domain of expertise from that of theological or philosophical matters. I think that this religious fanaticism of scientists is polarizing, and that is the heart of all the problems we have in our political system today, these identity politics and such. Polarization has not just happened in the political realm, as we see. It's also happened in the religious and scientific realms. When scientific jerks think that they can shame religious people into agreeing with them, I think this is just silly. Non-scientists are not stupid, and they just refuse to take the things that scientists say on faith. And for this reason, they might actually make better scientists than the scientists themselves, because they might not be so egomaniacal about naming every new observation after themselves. They would also be less inclined to worship silly men from history and more inclined to think for themselves on scientific matters while leaving religious matters to more historically grounded communities. These lofty matters of truth matter little to those who love power, and those who love control live in terror that the system will slip from within their grasp. If the few independent thinkers who understand unified frameworks for physics are localized in hotspots that speak different languages, coherent motion will not be able to disrupt the existing power structure and allow disruptive bursts of energy to escape. That is a key strategy in the social engineering of the scientific community, or of any community. In the coronavirus panic, for example, you want to prevent those who have an accurate sense of how the pandemic could transform society from communicating with one another, because their information can disrupt the system and cause unpredictable collective movements. And there's one thing that control freaks hate, and that is unpredictability, even if it is required to release energy from the system. You've got these tower blocks where they try to quarantine people, and if you don't give those people a pressure valve, you get little, rebellious movements. I think they should, whenever you have to quarantine a large group of people, you should give them a space to blow off steam, like a circus tent or something. I don't know. There is, unfortunately, every hot spot in a system has a melting point. the superconducting hotspots begin to break down the substrate and change how energy flows, reducing the amount of energy absorbed by the substance. And sometimes it is cruel to allow or to enable a hotspot to overheat, especially if that hotspot is a metaphor for a person. If you think in anti-de Sitter space, a hotspot is a black hole. Isn't that strange? You can invert everything. It's like the negative of a photograph. When I was a student, I never asked myself why Anderson got to name the concept of light localization after himself. It seems so general. Today, I'm a bit curious about how he turned himself into a central figure in the materials science community and how he was able to popularize an anti-reductionist approach. Maybe his greatest discovery was that you can localize information propagation and destroy a community's ability to communicate if you encourage everyone to egomaniacally name simple things after themselves. This is why I try to decode the many languages of physics in my blog posts and describe physics in simple words that have unambiguous meanings. We all try to do this to a certain extent, but I think we all need to try harder to repair the degenerated physics landscape cultivated by men like Anderson and Gell-Mann. Thank you for watching, and I encourage you to click on the blog post to find more topics that relate to this issue. Until next time, please tune in for the next video.